Hey, welcome back to Math with Patrick. Today is September 1st, and we're solving problem number 244 from the Daily Epsilon calendar. And since today is the 1st, the date is 1, and the answer to these problems always matches today's date. So we should be expecting the number 1 at the end of the problem. As a little aside, I have done a little bit of group theory before, but not a lot. And so I had to learn a lot about this problem before talking about it. Maybe if you're an expert in group theory, you know more than me, and maybe your solution will be quicker and more elegant. I'm going to talk about my solution as if you had the same amount of information as me starting out, which is like a little bit, but not a lot. So bear with me if you know more about group theory than me. Sorry. We need to find the number of proper normal subgroups of A5. And then it gives us a definition of what A5 is, the alternating group on 5 elements. So what the heck? First things first, what is a group? A group you can understand as just a collection of things. So for example, the group like 1, 2, 3, you could just think of as the numbers 1, 2, and 3. But then groups also need some kind of operation to actually be called a group. And so we could try to stick in the operation plus and see what happens. And there's one more rule that groups need to follow, where that once you apply this operation on two of your things in the group, it needs to come back to the same group. This is the closure property, where if we're trying to combine some things that are already in our group, we need to result right back to where we started. So if I tried saying, hey, here's my group, the numbers 1, 2, and 3, and the plus sign, well, I have a little bit of an issue when I try to add 2 and 3 together and I get 5. This number is not in my group because it was just 1, 2, and 3. So maybe you're thinking, well, what's the big deal? Couldn't you just slot the number 5 in here? And I guess technically I could, but then I could grab like 1 and 5 together, add them together, and get 6. And then the problem here is that I'm just explaining the integers, which is fine. The integers are a group with the operation of addition, but that's an infinite group. And at least for today, for this problem, we're talking about finite groups, or groups with a limited size. So the solution here, if I really wanted to talk about a group with 3 things in it, I could just figure out the remainder of this number after dividing by 3. So if I found the remainder after dividing by 3, that's why I'm using the little percentage sign for modulo. 5 mod 3 is the same thing as 2. So in this particular group, 2 plus 3 would result just back to 2 again. And so I am having this closure property as long as I think of 5 and 2 being the same thing here. And then I could grab any other 2 numbers and it would just bring me right back to this group again. Like 1 and 3 added together is 4, but under the idea where I'm finding the remainder after division by 3, 4 and 1 are the same thing, and so I'm going right back to my group. So that's what it means by group. And what it means by subgroup is sometimes you're allowed to pull just a few numbers from a previous group and try to see if it plays this by like the same rules, essentially where I still have the same operator. I'm still having the idea of like dividing by 3 and taking the remainder. And I want to see if this subgroup is closed, as in just composing 1 and 2 together will bring me just back to either 1 or 2. I could even pull the same element itself. So I could try 2 plus 2. That's going to give me 4. With the idea of dividing by 3 and taking the remainder, that's the same thing as 1. And so far, it seems like my group is closed because I went right back to the number 1. But if I do try to do, say, 1 plus 2, that's going to give me the number 3. And then 3 divided by 3, that remainder is 0. So I guess technically, to start out, maybe this should have been the group 0, 1, 2. Sorry. Since I got the result 0, and that is something back from my original group, not this potential subgroup, I know that this subgroup actually doesn't work. Subgroups themselves need to be closed. And so if I'm able to grab these 2 values, use my operation, and get something else that's no longer in this potential subgroup, it's no longer valid. And so 1, 2 is not a valid subgroup because 0, I was going to say 3, 0 has to go back in there as well. Other vocab things, every group is a subgroup of itself. So this one right here is totally a fine subgroup for the group itself. It's just no longer considered a proper subgroup because proper subgroups are considered to have a smaller size or cardinality than the actual group. And so even though this is a subgroup, it is not a proper subgroup because it's just the same group as before. One example of a proper subgroup would just be taking this 1, I think. Actually, no, never mind, because then I can compose 1 and 1 and get 2, and so I'd have to stick 2 in there. And then now I have 1 and 2, and so I'd have to stick 0 in there again. Sorry, I think the only proper subgroup of this guy would be just with the element 0, because with 0, I'm kind of stuck just getting back to where I'm at, 0, and I can't figure out how to get either of the other elements from the big group into my subgroup. So here is an example of a group, and it's one and only proper subgroup. Something kind of important to know is that the cardinality or size of any subgroup always divides the cardinality or size of the bigger group itself. So since this has a size of 3, any possible subgroup of this group is either going to be of size 3, which we saw, because 3 divides 3, or the only other option is a group of or subgroup of size 1. And I happened to find an example where that worked. So I think we now have a good understanding of what a proper subgroup is. Though we need to talk about what A5 is, this idea of the alternating group. Before we talk about A5, I think we need to talk about the symmetric group of 5 elements. The symmetric group takes 5 things. Let's just call them 1, 2, 3, 4, 5. And the symmetric group describes all the different ways that you can scramble these elements into a different order. So this idea of swapping my 2 and my 1 is an element in my symmetric group. Now, it's not this ordering that's an element, but rather it's the way that I swapped them is an element of this symmetric group. So I could swap the 1 and the 2. I could do a swappy swappy where I grab more of my elements. Like maybe I want to bring my 1 over here, and my 4 right there, and my 2 right here, and my 3 right there, and my 5 over there. And so this scrambling is another example of an element in our symmetric group on 5 elements. And so the only difference between the symmetric group and the alternating group is that the alternating group has like one more additional rule. And I'll just kind of write out another example to express what that rule is. In our symmetric group, we are totally allowed to just swap 2 elements like this. And so this swap is an element of the symmetric group with 5 guys right here. But this is actually not going to be an element of A5, my alternating group. A5 has a specific rule where I need an even number of these single pair swaps to be allowed to be a part of this group. So this switch isn't an element in A5. But if I do another swap, like say I swap this 1 and this 3 now, so the 3 goes there, the 1 goes there, the 2 stays put, the 4 and the 5 stay put. Now this is a totally valid element in A5 because I was able to create it by composing 2 different swaps. So the 1 went here, the 3 went here, the 2 went there. And this is something called a 3 cycle, just because the 1 hopped over to this spot, and the 3 went there, and the 2 went there. And then so we have 3 elements that kind of swapped their positions. So any 3 cycle is a totally valid element in A5. Also, we could like swap the 1 and the 2 and then like the 3 and the 4. So we could get some kind of element in A5 that looks kind of like this. because I'm composing it with an even number of swappies. The instant that I try to include a third, like this and this, then this kind of grouping of swaps is no longer an A5 because that's an odd number of swaps on my positions. So in addition to 3 cycles totally being fine as an element of A5, I could also have kind of 2 pairs as an element of A5. The last type of element in A5 is a 5 cycle. That means taking the kind of original starting point and then trying to move the numbers around without kind of repeating myself until I have to. And so one way to write this idea is that the number 1 went to the number 4, then 4 went to the number 2, then 2 to 5, then 5 to 3, and then 3 back to 1. And so this notation right here expresses the idea of bringing, 1 to 4, then 4 to 2, then 2 to 5, then 5 to 3, and then 3 back to 1. Using this notation for, say, this example right here, this tells me that I should swap the numbers 1 and 2. I should swap the numbers 3 and 4, and then I should keep 5 by itself. And so I don't really need to write that part because if it's not there, we assume we're not touching it. And then this first example that I was mentioning, this 3 cycle, I could write that as 1 going to 3, 3 going to 2, and then it's assumed that 2 goes back to 1 with this notation. And then once again, I don't need to write the 4 and the 5 because those weren't moved. So here are some potential elements in A5. I could have 3 cycles. I could have this kind of like 2 disjoint 2 cycles. And then I could have some 5 cycles. And I think these are all the valid elements in A5, except for also like the identity, which basically means the do nothing operation. And so we won't be cycling things around, our numbers 1, 2, 3, 4, and 5 can just stay put. And that is a totally valid element of A5 because you could imagine it's the same thing as me swapping 1 and 2 and then swapping them back. And so since I have 2 swaps, I swap there, swap back, it is a valid element of A5. I think it'd be valuable to know the cardinality of A5. And the quick way to do it is actually to learn the cardinality of the symmetric group on 5 elements. Essentially, this is just asking how many different ways can you scramble 5 things. Each different scrambling is another element of the set. And so the question of how many ways can you rearrange 5 objects is just exactly 5 factorial. So if I wanted the cardinality of S5, it would be 5 factorial. And then this is kind of like a trust me moment where exactly half of the elements in S5 are going to be considered even, where we have an even amount of singular swaps, and exactly half are going to be odd, where I have an odd amount of single swaps. And so 5 factorial is 120. That's like 5 times 4 times 3 times 2 times 1. And if you believe me that exactly half are even and half are odd elements of S5, then it would follow that the cardinality of A5 is 60. Just to prove that in one more way, we have exactly one identity element. There's just one thing that does nothing. Then we can count the number of 3 cycles we have. Essentially, we need to think, okay, how many different ways can we choose from 5 objects, choose 3 of them? And then so this kind of looks like me selecting, say, 3 kind of random numbers from our collection. And then I have 2 options from these 3 elements to create a new element in A5. As in I could swap the 2 to the 4, the 4 to the 5, and the 5 back to the 2. Or I could have done that in reverse, where I could have gone 2 to the 5, then 5 to the 4, then 4 back to the 2. And so each time I choose 3 out of the 5 objects, I do have 2 new 3 cycles that I haven't looked at yet. There's also technically, after I choose these 3 objects. I could also do nothing with them, but I've already counted that idea with the identity element of A5. So this expression right here counts the number of 3 cycles I have. I'll just put this 1, 2, 3 here to remind myself that this is the number of 3 cycles. The number of ways to choose 3 things from 5 objects, I'm just using the formula for the choose function right here. This 3 factorial can kind of simplify with that 5 factorial. This is just the number 2, so I'll simplify that. And then I have 10 here times 2, that's 20. So we have 23 cycles that are in A5. Here I can count the number of ways, or number of kind of 2 disjoint 2 cycles by, let's say, how about doing, we could choose which number is left out. And so there's going to be 5 different options for just leaving a number out. And then once we have these 4 numbers to kind of pick from, let's imagine that we are swapping the position of 1 and one of the other numbers. Say if we do 1 and 2, that kind of decides that 3 and 4 are going to be swapped with each other. And then likewise, if I choose 1 and 3, that kind of then therefore decides that 2 and 4 are swapping with each other. And then lastly, if I pick 1 and 4, then that automatically decides that 2 and 3 are going to be swapped with each other. So after I have 5 options of leaving a number out, then I have 3 options of where I could assign this 1 to go. And then that automatically chooses the rest of it for me. And so 5 times 3 gives me the number of 2 disjoint 2 cycles, that's 15. And then counting the number of 5 cycles, I think is just going to be 4 factorial, and I'll try to explain why. Basically, we could think of maybe a visualization actually here, where we have 5 different elements, and we're trying to figure out where to scramble them. I could take this first element and put it in any of these 4 spots. So any of these 4 spots is going to be valid. Let's just pretend I put it here. And since I had 4 options, I'll just put a 4 there. Then this next branch could go anywhere else. I have 3 options now, so now we have times 3. And then maybe you kind of see where this is going. I now have 2 options. I could go here, or actually, let's just go there, or there. So there's 2 options for that move. And then finally, I'm kind of just forced to go here and then back here to complete my 5 cycle. And I could have started at any of these points. So it's not like I had 5 options at the start, right? I didn't have 5 options to choose what point I was going to be at, because if I chose to be there, I could very well just be caught in the same 5 cycle that I just wrote here. So with 5 items, there are 4 factorial 5 cycles that are possible. That's 24. And if we add up all of our elements, 1 plus 20 is 21, plus 15 is 34. No, 36. And then 36 plus 24 does get us back to 60. So these are our elements in A5. We have a bunch of 5 cycles, a few double pairs, and a little bit more of these 3 cycles to contend with. Okay, finally, what does it mean to be normal? The definition of a normal subgroup is that, say we find some normal subgroup, let's call it N, where it is a subgroup of A5. There's essentially some rules that the elements of N need to follow. Namely, for the element N, little n, in our normal subgroup N, if I decide to put some element, let's just say G, from A5 and apply it to the left, and its inverse on the right, this new composition right here must still be in my normal subgroup N. And kind of the way to understand what's going on is let's say we just think of just numbers again for a sec. Let's take say N could be the number 5. Usually if you apply some number, let's say 2, and its inverse, I want to think multiplicative inverse right now, 1/2. Usually it's the case that you're just going to get the number back that you had, right? 5 and 5 here are the same. And so for a lot of operations out there, when you apply some operation and its inverse, you just get back to where you started. But our alternating group is a little bit strange, actually. where if we try to like place, some kind of element in our n and essentially throw it through the ringer of doing another element and its inverse, we could figure out whether or not our normal subset is a true subset or a proper subset, or rather, we might just find out that we're going to generate our whole A5 again. So that's kind of my goal, where I'm going to pick, well, let's say we're inventing our normal subgroup. Let's say I really, really want maybe one of our 3 cycles to be in our normal subgroup. So I'll say like there's an element in here, and let's just say it's the 3 cycle 1, 2, 3, for example. Now, I need to throw it through the ringer. I need to basically find some element and its inverse, and these ones are allowed to come from the whole set. And the idea is that hopefully we get something that goes right back into our normal subset. So the most obvious inverse pair to me is one of these like double 2 cycles. And the reason being is that like once I apply the swap of 1 and 2 and 3 and 4, if I just apply this exact same thing again, I'm going to go right back to where I started. Or in other words, I'm not going to do anything. Or in other words, that's the identity element in A5. So these elements in A5 are self-inverses of each other, because when you apply it once and then again, you essentially do nothing. So these are going to be kind of my testing values for G and G inverse from A5. And then I'm hoping that once I stick this 1, 2, 3, again, supposedly from my normal subgroup, that I get an element back from my normal subgroup. So now we need to think, how do we compose all of these different like swaps or inversions with each other? We could write out all of our numbers, 1, 2, 3, 4, 5, and then kind of read left to right where these numbers go. So this 1 is going to move to 2, 2 is going to 1, 3 to 4, 4 to 3. This is a 3 cycle, and so 1 goes to 2, 2 goes to 3, 3 goes to 1. And then we apply the inverse operation of the one before, and they just so happen to be identical. So 1 goes to 2, 2 goes to 1, and then 3 goes to 4, and 4 goes to 3. So ultimately it looks like 1 went to 4, 4 went to 2, and 2 went to 1. Hold on, I was writing that wrong. 4 went to the position 2. There we go. Then the number 2 goes to the position 1. 3 kind of hops around and ends up back where it started, and 5 we didn't even touch. And so to me, it looks like we have a 3 cycle where 1 went to position 4. And so I'll write it out like this. So 1 went to position 4. The number 4 went to position 2. And then the 2 went back to position 1. So what this tells me is that if we assume we just have like a 3 cycle in our potentially normal subgroup N, then I do need to also include this guy, 1, 4, 2. And also for it to be a subgroup, I need to find inverses of the elements that we already have. So I need to find the undoing operation. So 1, 2, 3 actually doesn't have its inverse yet in our normal subgroup. 1 going to 2, 2 going to 3, and then 3 going to 1 can be undone by thinking of it in reverse. So instead of 1 going to 2, we need to think about 2 going back to 1. And then we need to think about 3 going back to 2. And then we need to think about 1 going back to 3. And that's what this notation does. And just because I like to kind of have my 1 at the start, I can't actually put this 1 right here, and that still expresses the idea of 1 going to 3, 3 to 2, and then 2 to 1. So just as a little note, a 3 cycle is inverse with the pair where you flop the last 2 values. So it looks like maybe our normal subgroup N is going to contain 1, 2, 3. Also, its inverse, 1, 3, 2. And then we created 1, 4, 2 by just kind of finding some elements here from A5 and applying just the definition of normal subgroups to it. And then we could also find its inverse, 1, 2, 4. And then since this is supposed to be a subgroup, we can then compose these ones with themselves and see what happens. So these are all elements of my subgroup, and so I could combine these two together and see what happens. So reading it like this, I can see that 1 goes to 2, and then 2 goes to 1. So 1 actually isn't even touched if I apply these two together. Thinking about the number 2, 2 goes to 3, and that's it. So I could say 2 goes to 3, 3 goes to 1, and then to 4, so 3 goes to 4. And then 4 goes back to 2. So cool. From these 2 3 cycles, I can generate another one. I also need this one's inverse, which we know that we can just swap the last 2 numbers to find the inverse. And I think let's compose these two. 1 goes to 3, and that's it. So 1, 3. 3 goes to 2, but then 2 goes to 4. And then 4 goes back to 1. And then, let's see, 2 shouldn't be touched, right? Because 2 goes to 1, and then 1 goes back to 2. And then we could also get the inverse of this one by switching the 4 and the 3. And all of these, I believe, are distinct. Just a little quick look. Yeah, okay, because like this one doesn't have the number 1. This doesn't have the number 2. And then this doesn't have the number 3. And then these don't have the number 4. So we have 8 3 cycles, and interestingly, these are actually all of the 3 cycles that you could possibly get with 4 numbers. And the 4 numbers that we're seeing here are the kind of the same 4 numbers from these 2 elements. Again, some element from A5 and its inverse. And so you could probably assume that if I swapped out this 4 for, say, the 5 that we do have from A5, then the 5 is just going to populate in every single place that you happened to see A4 from before. Maybe I'm actually wrong on that, but I'm pretty sure that if we just grabbed another value from A5 that did include the 5 in it, then we would get all of our other 3 cycles, including the ones that include the number 5. So what does this mean for normal subgroups? Basically, it means that if we grab one 3 cycle, we have to grab them all. And then I also know something where if you have all of the 3 cycles of a alternating group, that generates the rest of it. So if we had, say we like tried to just do a subgroup with all the 3 cycles, there is a theorem out there that essentially states that this would then generate all of A5 based on the idea of just trying to compose all those 3 cycles together. And that's not what I want. I don't want to generate all of A5 because I want a proper subgroup. I don't want the exact same group that I had before. So that tells me if it's a normal subgroup, I can't have any 3 cycles. And so none of these are elements in our potential normal subgroup. Now we can assume that any proper normal subgroup just doesn't have any of those 3 cycles. So maybe we could start with one of these 2 cycle pairs. And it doesn't really matter that I'm picking kind of like the obvious one here. Any operations that I do to this one, I could probably find just other numbers that would work for other 2 cycle pairs. So it's not like this one is unique or interesting in any way. Whatever I do to this one, I could just do similar things to any of the other 15. And I think I found a solution, and these are the first kind of G and G inverses that I'm going to pick from A5. And let's just see if this works out. We saw earlier that just flipping these last 2 numbers finds the inverse of a 3 cycle. So composing these all together, 1 goes to 4, and then 4 goes to 3. And then 3 goes to 4, which goes back to 1. Cool. And then 2 goes to 1, which goes to 5. And 5 goes to 1, which goes to 2. We're done. And we should just check that 4 doesn't do anything. 4 goes to 5, and then back to 4. Cool. Now let's take the same element that we had, this 1, 2, and then 3, 4, and I'm going to apply a different G and G prime. Let's do 1, 3, 5, and then 1, 5, 3. Again, both 3 cycles and also inverses of each other. 1 goes to 3 and then to 4. 4 goes to 3 and then 1. 2 goes to 1 and then 5. And then 5 goes to 1 and then 2. And then we should double check that 3 doesn't move. So 3 goes to 5 and then back to 3. Cool. So with this one element and applying certain g's and their inverses, I was able to create 2 other elements. So both of these should then go back into our subset, or a subgroup rather. Sorry. So if they're both in our subgroup, under the closure property, I should be able to compose both of those and get something else in our subgroup. So there's the first one. There is the second one. 1 goes to 3, and that's it. 3 goes to 1, and then 4. And 4 goes back to 1. And then if we do anything with the 2s and the 5s, we can just kind of see that they swip and then swap back. And so here, I was able to start with one of these 2 cycle pairs, and then I generated 2 others, and from those 2 others, I got a 3 cycle. And like I said, this one isn't special. It could have been any other 4 numbers, and then there probably are some special values here and here to get these 2. And I think the idea is that we find these 2 things being copies of each other. And I think that happens to be important for this part of the proof. Regardless, starting with one of these 2 cycle pairs, we were able to create a 3 cycle, and then that one 3 cycle would generate the rest of the 3 cycles, and then that would generate the rest of A5. And so we have an issue here where the 2 cycle pairs aren't good either, because then we just get back to the whole entire group. So the last thing we could possibly do, well, technically second to last, is try to pick a 5 cycle first, and hopefully this stays contained with just 5 cycles, so we don't kind of break out and get one of the other 2, because if we get another one of the other 2, we know that we're generating the whole group again. So let's just put on a G and a G inverse on 1, 2, 3, 4, 5, and work through the numbers. 1 goes to 2, 2 goes to 3, 3 goes to 2. 2 goes to 3, 3 to 4, 4 goes to 5, 5 goes to 1, which then goes to 3, and then hopefully 3 goes back to 1, 3 to 1, 1 to 3, and then, wait a sec, 3 to 1, 1 to 2, there it is, and then 2 goes back to 1. Good. Okay. And then so now we have another element that's supposed to be in this subgroup. And I think what I did to this one is I just composed it to 1, 2, 3, 4, 5 2 more times. And then this caused a 3 cycle. So let's see if it's going to work out. 1 goes to 2, which then goes to 3. 3 goes to 1, which then goes to 2. 2 goes to 4, which is then 5. And then 5 goes to 3, which then is a 4. And then 4 goes to 5, which goes back to 1. Good. And then I composed this new one with 1, 2, 3, 4, 5 again. And I think this is the last one. I think this will create the 3 cycle. 1 goes to 3, which then goes to 4. 4 goes to 1, which goes to 2. 2 goes to 5. 5 goes back to 1. And then we should double check that 3 and 5 don't do anything. So 3 goes to 2, and 2 goes back to 3. That's good. And then 5 goes to 4, which then goes back to 5. Cool. So by starting with, I know not like a random 5 cycle, but like I said earlier, any of these 5 cycles, I could have just found the right G and G inverse. And after composing it with a few of the things that I generated, I got to yet another 3 cycle that's supposed to be in our normal subgroup. So this is where my proof ends. In any of these cases that we grab any of these 5 cycles, 3 cycles, or the pair of 2 cycles, we're always inevitably just going to recreate all of A5 with kind of this G and G inverse rule. The only other thing we could do is just grab the identity scrambling or permutation. And then if we do G identity, G inverse, the identity doesn't really do anything. And then any permutation and its inverse are going to get back to the identity, which is the one and only thing in our subgroup. Real quick, before we finish the video, I at least want to give an explanation as to why, if we have the collection of all 3 cycles, we can generate all of A5. Let's imagine that we have just some element from A5, let's call it like little a. And since it's in A5, we know that it's composed of an even amount of inversions. And so we could write out A kind of looking like maybe 1, 2. And so each of these little arrows is an inversion. And we're going to have an even amount. Not sure exactly how many, but let's just say that many. And either our pairs of inversions are already just going to be 3 cycles. Like if we do 1, 2, and then 2, 3, this reduces to a 3 cycle. So that's done and easy. Or we're in the case where our 2 cycles are disjoint. So maybe it looks like that 1, 2, 3, 4. But anytime that you have disjoint 2 cycles, you can just rewrite it as a pair of 3 cycles. So I think the easiest example is just 1, 2, 3, and then 2, 3, 4, where 1 goes to 2, and then 2 goes to 3, 3 goes back to 1, and then 2 goes to 3, and then 3 goes to 4, and 4 goes back to 2. So I guess this one isn't exactly that one, but you could assume that if we could rewrite this pair of disjoint 2 cycles as a pair of 3 cycles, then we could do the same for this one. So no matter what, as you work through your many, many pairs, possibly many pairs of inversions, you can always find some number of 3 cycles to write it as. And since we have all 20 of them, we aren't worried about if we have or don't have any of these building blocks. At least in this example, this problem, once we had one of the 3 cycles, we were able to generate all of them. And then this last little bit of the proof is just showing that once you do have all of them, you can write any element of A5 with just 3 cycles. So if we do want a normal subgroup, it needs to either be A5 or just the kind of trivial subgroup of only the identity element. And then if we need a proper subgroup, then we're forced to only take the kind of the trivial subgroup there. So we have the one and the only one subgroup, and that means we're done. Thanks for coming along for this longer video, and I'll see you tomorrow. Bye.